Hey you guys, today's lesson is about the layers of the earth. And so we're going to go through a slideshow called Journey to the Center of the Earth together. Okay, for today's activity, you're going to need the layers of the earth diagram. If you picked up your packet at Camachin, it's page 9. You have two other options though if you have not picked up your packet. You can print out the following page, which will be this diagram. Or if you don't have access to a printer, you can take a blank piece of paper and you can just sketch out this diagram. Don't worry about writing all these words on your sketch. Just sketch out this kind of pie-shaped piece here, and you can use that. And it doesn't have to be perfect. You're also going to need something to color with. Colored pencils are preferable, or you can use crayons, you can use markers, you can use highlighters. Just something to color in would be great. If you don't have anything to color, that's okay. You can just do the notes. Okay, so here's the page. So if you want to print out this diagram, then just print out this one slide. Okay, so I'm going to read through this and I'll let you know what you need to do on each part of your diagram. So we all call the Earth home, but did you ever think about what our home is actually made of? The planet is approximately 6,400 kilometers from the surface to the center. But what makes up those kilometers of Earth? If we could travel through the layers of the Earth, what would our trip be like? In order to make this trip, we would need a special vehicle that could travel through both liquid and solid rock, and that could withstand intense temperature and pressure changes. The deeper into the center of the Earth, the hotter it is and the more pressure we will face. And pressure means the more the other layers of the Earth are pressing down on you. Okay, so what's the deepest humans have ever dug into the Earth? So known as the Kola Super Deep Borehole, the deepest hole ever dug reaches approximately 7.5 miles below the Earth's surface, or 12,262 kilometers, a depth that took about 20 years to reach. It's not a very wide, like you couldn't fall into this hole. It's like a drill hole into the Earth. The hole was intended to go as deep as possible, which researchers expected to be around 9 miles. So they thought that they could go 9 miles, but they only went 7.5. But the scientists and engineers were forced to give up when they hit unexpectedly high temperatures. At 7.5 miles below the surface, the billion-year-old rocks there are at temperatures of around 180 degrees Celsius, which is 356 degrees Fahrenheit. This was almost twice as hot as they'd predicted. And so that intense heat made it really hard to dig any further with their drill. Okay, so of course you're wondering to yourself, well, if we've only gone 7.5 miles, how do we know what all these different layers of the Earth are? So how do scientists study Earth's interior if we can't get through it? Seismologists are geologists who study seismic waves to learn about Earth. Studying the behavior of earthquake waves to gather data about Earth's interior is similar to using sound waves to see inside the human body. So if you've ever seen like pictures, like ultrasound pictures of a baby inside of a woman's body, like, oh, here's, ultrasound to kind of make sure the baby's okay. That's similar to what seismologists do with earthquake waves. Observing seismic waves or earthquake waves allows scientists to infer or figure out indirectly images of Earth's interior. Data has shown that seismic waves bend when they encounter sharp changes in density. There are different kinds of seismic waves known as P waves, which can travel through liquids and solids, and S waves, which can only travel through solids. Studying these waves helps seismologists theorize the composition, thickness, density, and phases of the 4 layers of the Earth. Okay, so if an earthquake takes place right here on the Earth, it sends out waves. It sends out S waves and P waves. Only the P waves can go through liquids, and the S waves get bounced off of different layers. So by watching what happens on the surface of the Earth in other places when an earthquake takes place, geologists have an idea of how thick these different layers are and whether they are solids or liquids. Okay, so let's start our journey to the center of the Earth. In order to make it through, we have to start with the part of the Earth that we live on, which is the outermost rocky layer called the crust. This layer can range from 5 to 40 kilometers thick. the thickest sections occurring at mountain ranges, like right here. And the thinnest sections are where the ocean floors are. The crust is separated into two parts. We have oceanic crust, and that is consists mostly of dense rock that is like basalt. Dense meaning that it is going to be heavier for the same amount of continental crust. So when the two of them are going to meet, the oceanic is going to float deeper and the continental is going to float higher. The crust is separated into two parts. Oceanic crust, which is ocean floor, which consists mostly of dense rocks. Oops. Which consists mostly of dense rocks such as basalt, and continental crust, mostly of lighter and less dense rock like granite. So at this point, you would pause the video and color the ocean blue. That's the wavy part here, that's water. The oceanic crust is under the ocean, and we're going to make that dark brown. And the continental crust, which sticks out of our ocean, we're going to put that as light brown. Now, if you don't have these exact colors, that's okay. You can use other colors, and don't worry about the labeling quite yet. We're going to do that at the end. Okay, so now we're going to come to a boundary. Above this boundary, the rocks of the crust, below a layer of the hot rocks of the mantle. And that is this boundary right here. Together, these form a rigid, rocky layer of earth known as the lithosphere, which averages about 100 kilometers thick. We continue into the mantle where our vehicle encounters a hotter, softer material that is under increasing pressure. This must be the asthenosphere, the soft, hot, plastic-like layer of the earth that is constantly flowing slowly by convection currents. Pieces of the lithosphere float on top of the asthenosphere, and another solid layer of material lies below, making the mantle nearly 3,000 kilometers thick. Okay, so this layer is the crust. This layer is the mantle. However, the bottom of the crust and the top of the mantle are the lithosphere. Go ahead and label that. So this right here is a lithosphere, and that is rigid and solid. And that would be, if you've ever heard of the continental or the plate tectonics or tectonic plates, that's what those are. Underneath the lithosphere is the asthenosphere, and you can see that there are motion arrows going on. So this is kind of moving. It's a really thick liquid, kind of like maybe taffy. If you've ever thought about taffy or putty, that's the asthenosphere. And the asthenosphere is moving around, and the lithosphere is sort of riding on top of that, floating on top of that. And that's where we're going to start talking about plate tectonics at some point in the next couple of weeks. Down here is the solid lower part of the mantle. Okay, so at this point, I want you to label the lithosphere. That's right here. Label the asthenosphere. It's right here. By the way, these gaps in the layers of the earth don't really exist. That's just helping us with our diagram, with our model, but there's not really gaps of air or space between those layers. Okay, now go ahead and color the upper mantle yellow. Remember, that's part of the lithosphere. The middle mantle light orange, which is also the asthenosphere. And the lower mantle is just orange, and that's the bottom layer of the mantle. Okay, finally, we've made it to the core. So we've gone through the crust, the mantle, and now we're at the core. Phew, it's so hot down here. There are two parts of the nearly 3,500 kilometer thick core. We have a liquid outer core and a solid inner core. The iron and nickel material in both layers of the core make up about 1/3 of the Earth's mass, but only about 15% of its volume. The core is just slightly smaller than the moon. The molten metal outer core flows like a thick liquid, but there is so much pressure on the atoms of the inner core that they are pressed together into a dense ball of solid metal. We should probably get out of here before the enormous pressure and 5,000 degree Celsius temperature turn our vehicle into a solid ball too. Okay, so this is super dense in here. It is iron and nickel. So it makes up most of the weight or the mass of the Earth, but not very much of its volume. So this is a little bit out of scale. So the outer core is liquid, and the inner core has so much pressure on it that the material has solidified, so it's solid. Okay, so I would like you to color the outer core a red-orange, color the inner core red, and then we're going to add some notes. So I want you to write on here that the deeper you go into the earth, the hotter and the more pressure there is. I want you to label the crust, the mantle, outer core, inner core, and then there are some other notes here. So the oceanic crust is more dense and it's made of basalt. The continental crust is less dense and it's made of granite. That's going to be really important when we start talking about plate tectonics. The crust is 5 to 40 kilometers thick. The lithosphere is a rigid, rocky layer that's 100 kilometers on average thick. The asthenosphere is soft and putty-like, and it has what are called convection currents, so it's moving in here. The mantle in entirety is 3,000 kilometers thick. The outer core is made of liquid iron and nickel. The inner core is made of solid iron and nickel. The whole core is 3,500 kilometers thick and an average of 5,000 degrees Celsius. Okay, so after you've got everything colored and you've added your notes, you are finished. Then you're going to take a photo of your finished diagram, upload the photo to Canvas, and submit it.